All right, guys, we're going to finish up our notes by talking about pH. And maybe this is something that you have heard about before. Chances are you might have even tested pH of something before. If you have a pool, or you've been to somebody's house who has a pool, or maybe you've worked at a pool before, you know the little test strips or the water sample that you either dip the test strip in the water and read it against a scale, or you scoop up some water and you drop some drops in it and kind of give it a little shake and then read it against a scale. You're testing the pH of the water in that pool. And so the connection between water and pH, why do we spend time talking about it here, comes from this diagram. And so we know what a water molecule looks like. And as water molecules break apart and then reform, we can see what kinds of products they break into. And so if we follow the arrow this way, it shows us the reaction of breaking the water molecule down. One of the hydrogens sticks with the oxygen, and the other hydrogen sort of disassociates or pulls itself off. And then this arrow right here is showing that if you recombine these two, you'll create water again. And so in this back and forth relationship, water can disassociate, and then it can also reform. So we talk about pH because when water disassociates or splits apart, it creates these ions. So this OH, the oxygen with one hydrogen attached to it, is called a hydroxide ion. And then the remaining H, now carrying a positive charge because it lost an electron, is just called a hydrogen ion. And so we talk about this because when water breaks apart, water, as the structure that we have learned it, breaks apart, it forms these hydroxide and hydrogen ions. And the amount of OHs and Hs in a solution can really affect whether that solution becomes acidic or basic, which another term for basic would be alkaline. So I've written here that the hydroxide and the hydrogen ions that are formed when water breaks apart changes the acidity and alkalinity, that is the basic end of the pH scale, of the water or of the solution. And so pH is actually a measure of the number of specifically hydrogen ions that exist in a solution at any given time. And so a quick memory trick on, well, what is pH really measuring? We'll notice P, big giant H. pH is measuring the power of hydrogen, or the count of hydrogen ions in a solution as water is breaking apart and reforming and breaking apart and reforming. And so one thing that we should notice is hydrogen ions, the H plus, they're cations. They're positively charged because the hydrogen left its electron back with the oxygen and the hydroxide. And the more hydrogen ions you have in a solution, the more acidic that solution will become. If you have fewer hydrogen ions, the solution is opposite, basic. It becomes very basic. And so we measure this on a scale, and that scale is called the pH scale. And so you have this picture right here in your notes. There are a couple of additional slides here that we're going to talk about pH, and I know that your section of notes is not that big, so write a little bit small and feel free to annotate this right on or right around this particular pH chart. And so if we just pause for a moment before we move on, you'll see right here in the middle, the neutral range is always represented by kind of a greenish color, even on all pictures of the scales show green as neutral. And then even when you are doing things like testing pool water, you will see a little bit of a yellowish green color. And so 7 or 8 is neutral. The low numbers, or I should say the small numbers, 1, 2, 3, 4, are acidic, and the large numbers are your base range. And so this is a spectrum. So from neutral, working your way out, the further towards one you get, the more acidic the solution becomes, and the further out towards 14 you get, the more basic or alkaline the solution becomes. So let's talk about, or write down rather, what I really just said. So pH numbers, right? So the scale had numbers 1 to 14. pH numbers represent ranges of hydrogen ion count. So 1 to 6 are technically acidic, which means that there are more hydrogen ions than there are hydroxides. Because remember, the hydroxides didn't go away. They are hanging out in the solution. That's what happens when water sort of breaks apart. But if you have more hydrogen ions, you're going to be in the acidic range. And the bigger the difference, the lower the pH value becomes. So this picture right here shows a solution that has a whole bunch of hydrogen ions and just one little hydroxide. That would be a very acidic solution, a 1, a 2. If this picture showed, 5 hydrogen ions and 2 or 3 hydroxides, it would still be acidic, but it would be a little closer towards neutral, maybe a 4 or a 5. But on your chart, it's already written for you. If you want to bracket 1 to 6 are acids, 7 is neutral, which means there are roughly about as many hydrogen ions as there are hydroxides. And then 8 to 14 are bases. And so you can see over here, this is a basic solution where there's very few little hydrogen ions, and the rest are these hydroxides. So one thing to kind of catch yourself on and just be aware of, a lot of times students get pH and the scale sort of twisted around in their head, because actually a low pH number, a number of 1 or 2, actually represents a very high hydrogen ion count. And so just be aware that as you use words like high and low, what are you indicating? Are you indicating the actual pH value, or are you trying to talk about the count of hydrogen ions? So for example, under this picture, you can see a low pH value. If we say we are lowering pH, that means we are driving towards a smaller number. And the only way to do that is to add a bunch of hydrogen ions. Reverse concept applies. If we are increasing our pH value, that means we're driving more towards 13 and 14, making the number larger on the scale. And the only way to do that is to actually remove hydrogen ions and lower that particular count. So most living things can only exist within a very narrow range on the pH scale. And for us, most of the systems in our body, most of the enzymes operate, most of our internal structure hovers around the neutral value. Our blood must be relatively neutral. That's very, very important. And there is a buffering system that we might talk about in class that helps us to maintain a blood pH that's relatively neutral. However, there are some environments in our bodies that do require a deviation from the narrow range that everything else exists at, right? So pretty much everything is a pH in our body and our systems, a pH of 6.4 to 7.4, except in our stomach. And you know that there are acids in your stomach that are helping with the digestion process. And so there are a few select areas in our body that have a really specific pH value that is very different from the general 6.4 to 7.4. But what I will say about that, we will learn when we talk about things like enzymes. Your stomach is an environment that is prepared for acidic contents. And so there is a unique secretion that the lining of your stomach makes and produces to kind of protect it so that it doesn't get eaten away by those digestive enzymes. So by and large, most of the human living systems that I'm talking about are relatively neutral. However, be aware that there are some pockets in our body that do deviate from that neutral range. when you look at the scale, this is still in the scale section. I think this is our last slide. What I want you to see is that the pH scale is actually a logarithmic scale. Now, without getting too far into the weeds, the big thing that we should consider when it comes to a logarithmic scale is that each time we change number values on the scale, it's not just 1 or 2 or 3 times difference. It's actually every time we transition numbers, it's a 10 times change in the concentration of hydrogen ions. And because it is a negative logarithmic scale, that means that each time we move, we are producing number values that are smaller and smaller and smaller and smaller and smaller, which should make sense because we know the most hydrogen ions exist at these pH numbers up here. But as we progress towards 14, there are fewer and fewer and fewer hydrogen ions in the solution. So let's look at this. A pH of 1 really has 1 times 10 to the negative 1 concentration of hydrogen ions in it. So there are 0.1 hydrogen ions in a particular measure of that solution. If we transition to a pH of 2, notice that it's not twice as less, or it is 10 to the negative 2, which is 0.01 hydrogen ions per solution. So when we get together in class, this is actually what we're going to practice on our first day, just making sure that we understand that. But here is a very simple example of this concept in play. If I'm talking about a solution that has a pH of 4, something that sits right here as a pH of 4, how many more times, in this case, acidic, is a pH of 4 compared to a pH of 6? And so really I'm asking, what is really the difference in hydrogen ion counts between a 4 and a 6? And I've given it to you in X, in how many more times more acidic it is. So that was a really confusing, bumbly way. Here's how you would work something like this. If you're starting at a 4 and you're jumping to a 6, that means you're jumping 2 numbers. So that would be 10 times 10. Okay, so 10 times 10 is 100. And that's what we would write here in this blank, which then says a pH of 4 is 100 times more acidic than a pH of 6. If I had given you a 4 compared to a 7, that would have been 1, 2, 3 times that we are jumping on the pH scale. So that would be 10 times 10 times 10, which is 1,000. And so we would say that a pH of 4 is 1,000 times more acidic than a pH of 6. Again, we will practice that when we get together in class. Last thing that I want us to talk about is something called a buffer. So a buffer is a substance. Typically, it is a solution that is added to another solution that helps it resist a change in pH. And so this diagram I thought was kind of funny because here are the buffers that have been added to the solution. Okay, so buffers, keep in mind that whatever the solution is supposed to be, buffers try to help maintain that. And so in our body in particular, I mentioned our blood, buffers try to keep our blood at that relatively neutral value. And so buffers many work to maintain a neutral pH. Buffers are actually just really weak acids and really weak bases. So things that sit around a 5-6 would be a weak acid, probably more like a 6 would be a weak acid. And then substances that sit at around an 8 would be weak bases. And so those are buffers. And really, here is how you should think about it. If you have a solution that is becoming acidic, now think about if your solution is becoming acidic, that means the hydrogen ion count is climbing up, 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 up. We're getting lots of hydrogen ions in the solution. If you want to attempt to maintain that solution's pH, instead of letting it shift towards the acidic range, you would add sort of the counterpart, the opposite. You would add a weak base buffer. So if a solution is becoming acidic, you would add a weak base buffer. If that solution instead is becoming basic, what would you add? Think about. If the solution is becoming basic, you would add a weak acid buffer. So that's kind of in general what buffers are, and kind of what you add to what to maintain the pH of a solution. Now, here's how they actually work. Okay, so think about, this is our really acidic environment. And if I'm trying to lower that acidity, if I'm trying to prevent it from becoming acidic, we just said we're going to add a weak base to that. Well, the weak base is a base because it's got some hydroxides in it. And so if you dump in a bunch of hydroxides into this solution, those negative hydroxides are going to start to suck up and be attracted to these floating hydrogen ions, which then lowers the number of hydrogen ions in that solution, right? So weak base buffers act to buffer an acidic solution by absorbing all of these hydrogen ions, not all of them, many of the hydrogen ions, which then lowers the hydrogen ion count and pushes the solution more towards neutral. On the opposing side, if I have a solution that's pretty basic over here, I'm going to add a weak acid to it to try to drive it back towards neutral. Well, that weak acid is going to be a whole bunch of hydrogen ions, the weak acid will drop a substance into the solution that will push off its hydrogen ions, right? It's a weak acid, so it has hydrogen ions in the solution. And so now all the hydrogen ions dump in here and they're attracted to the OHs and they reform water, which drives the solution towards neutral. So here are the words to write down that describe the concept that I just talked about. Weak bases. So if I need to add something over here to this acidic solution, I'm going to add a weak base. How does it work? Weak bases will dump in here and they will start to absorb or attract these hydrogen ions to themselves, and that lowers the number of hydrogen ions in the solution and lowers the pH of, doesn't lower the pH. It lowers the hydrogen ions in the solution, which drives the solution back towards normal. So as you're writing your notes, instead of writing lowers the pH, we should say that it lowers the hydrogen count, right? That then pushes it towards neutral. Same thing here. I'm going to see the same thing. Weak acids. Weak acids would be added to a solution like this that's pretty basic. And weak acids will dump into the solution. They will release their hydrogen ions into the solution. They have hydrogen ions because remember, they're acids. And those hydrogen ions will bond to these OHs. They will form water, and that will drive the solution towards neutral. So again, quick correction. Don't put raising pH. That can be a little, it's incorrect. It doesn't raise the pH value. It will raise the hydrogen ion count in the solution, which will then bind to the OHs and create water. So we're going to do some work in class on buffers in general, and also going to do some of those practice problems related to the pH scale and making sure that we know the correct count every time we move numbers on the pH scale. So come with your questions for sure. I cannot wait to see you all first day of school in person.